All right. Good evening, everybody. This is going to be our stream, and so let's continue with the computer organization. I read this question before already, so we should be able to solve it. So total number of instructions are 6.4 into 10 power 8, and so this is the distribution of instructions. So this branch instruction. Is going to take 2 clock seconds, and alright, clock cycles are required per instruction, so it needs two clock cycles per instruction. So in total it needs 225 times 2 is 5 into 10 power 8, and 12 5 are 60, so 6 into 10 power 8, and 4, so 16 2s are 32, that is 33, so it is 66 if I'm not wrong. 4, yep, 66. So 6.6 into 10 power 8. Alright. And 13 3s are 39. So 3.9 into 10 power 8. It is going to need these many instructions. So the duration of the clock cycle. Alright. So it is going to need how many? 5 plus 6 is 11. 11 plus 6.6 is 17.6. 17.6 plus 3.9. 9 6 15. Alright, 1 and 21.5 into 10 to the power of 8 clock cycles needed, and it can be done in 6.3 seconds. So just do this 21.5 by 6.3. Let's open our calculator. Alright, we open our calculator, and 21.5 by 6.3, so 3.41. Alright, since this decreases, 30 seconds, I don't know, man. I don't know about this one, but we will see. Okay, did we mess it up somewhere? 2 into 2.5 is 4.5, not 5. 2.25 times 2, how much? Yeah, it's 4.5. Actually 2.5 times 2 is 5, so okay, that's a problem in arithmetic. And the 0.5 decreases, so 21 clocks per second needed. Alright, so clock, okay, total execution time, yeah, number of cycles times cycle time. This is why, alright. So total execution time is equals to, total execution time as 6.3, and the number of cycles as 21 into 10 power 8, and now you need to get the cycle time. So this one goes down. Yep, 3 nanoseconds, okay. That's good. Is instruction set architecture. Instruction set architecture contains instruction registers. ISA contains IRs. Uh-huh. Okay, that makes sense. Instruction set architecture, okay. For a direct mapped cache for bits are used as tag field. We need to look at this one. Okay. So for a direct mapped cache, you have a tag. Okay, but you have, offset and page size in OS. That is a different concept. Size of cache block is 1 byte. Now for main memory size, physical address is 16 bits. Okay. Tag bits, index bits, and block size. Main memory size is everything, okay? Cache memory. So let me get this right. Which block of main memory is currently stored? So this is main memory. Okay, we did this one before already. This block is indicated by tag bit, which cache line. index cache line of block. So we got tag, we got index, we got offset. So there is no information stored. The size of each block is 1 byte, so offset is 0. So index bit is 4 bits are used for tag and 12 bits are used for index. So 2 power 16 is size. So 2 power 16 is how much? 2 power 6k by how much? 2, 4, 8, 16, 64 kilobyte. And cache memory. So 12 bits for cache. 2 power 12 is 4 kb. 64 kb and 4 kb. Nice. Non-pipeline single processor computer system. The computer is connected to an external device that can interrupt the processor asynchronously. The processor needs to execute the ISR to send this interrupt. Yeah, basic question of interrupt service routine. It is executing some process, let's say P1. It needs to finish. No, it needs to save the contents. Okay, it is not a process. It is an instruction. Instruction complete because atomic. Don't confuse between what do you call it? Preemptive or non-preemptive scheduling. That is different. We are dealing with jobs over there, but here we are dealing with instructions. So finishes and saves and ISR 312. All right. Arithmetic operations. The data path can implement arithmetic operations involving two registers. So take this register, and here leave it. So one register and one immediate value. Yes, it is all right. Two immediate values. Yes, can only implement arithmetic operations. A, B, C are correct. Okay, so this is easy. 1,000,000 bytes and 16 kilobytes. I feel like I have done this question. 20-bit memory address and processor generates virtual address all the times and cache block is 16 bytes. The cache uses direct mapping. How many bits will be required to store all the tag values? Assume memory is byte addressable. So byte addressable means offset is 0. That's what we have understood. Memory system. So main memory is 1 million bytes and cache memory is 16 kilobytes. 20-bit memory addressing system. So cache block size is 16 bytes. So you need a 4-bit addressing system to store that. Okay, so is it going to be offset? So yeah, cache block size. So you are showing cache lines. So 4 and 0 and 20, 16 to store all the tag values. So 16 bit per tag. Okay, that makes sense. How many tags will be generated? Each all right. Where am I? So cache memory is 16 bits. Oh god. 1 million bytes of main memory, 1 megabyte. 16 kilobytes of cache memory. Okay. 20-bit memory enters the cache block size. How many of these will be generated? Okay, we need to know that one. Yeah, we got that. Okay, cache block size is that. Mm-hmm. Okay. Finds a byte within a cache block. Okay, okay. The tag bits are the remainder of the address. Index bits. अच्छा. Index, alright, number of cache lines. 16 KB by 16. So 1024. So 2 power 10. Offset. The offset finds a byte within cache block. Cache memory. Alright, alright. Cache memory. Cache block. Number of cache blocks is equals to cache line. Yeah, that's good. And 4. So 10 and 4, that is 14, and this is 6. So, and what was asked? So tag values, you need tag values here. So how many? You need 2 power 10 to represent all cache memory. That makes sense. Sixty-four general purpose registers and 50 distinct instruction types. An instruction type is encoded in 32 bits. Bits can be used to immediate operand. 64 registers and 50 instruction types. 32-bit. Okay. It can be used to store the immediate operand. Operand. I don't know. Opcode. add R125. So this is opcode and this is operand register. How many bits are needed? 50 distinct. So 6 bits for opcode. 64 is like 6 bits. And how many we got? 32 bits. 32 minus 16, that is 16 bits. Yeah, this is the sign that I will sleep. 6 plus 6 is not 16, right? That's why. Okay, we did this one already. We did this one, yeah. So, access time is 10 nanoseconds plus 0.5 into what is the access time including L1 cache miss penalty. So when cascading, okay. Mm-hmm. 180. So if you simplify this, you should get that. Wait, 0.05, sorry. 270. Okay. 1815 0270 27 37 Pfizer 18 11.852. Right, nice. Two 2010 gate, he's a veteran. Four megahertz processor. I will sleep after this question, by the way. If DMA controller can transfer 8 bytes in one cycle from device to main memory through cycle stealing at regular intervals, which one of the following? Wait, what? Yeah. Data transfer rate if 1% of processor cycles are used for DMA. 4 megahertz. So 4 mega 4 into 10 power 6 per sec. DMA controller 8 bytes per cycle. Which one of the following is the data transfer rate of the DMA? If 1% of the processor cycles are used for DMA, so 1%, alright, nice, 1%. So by 100, that is 4 into 10 power 4 cycles, and per cycle it can do 32 into 10 power 4. There is no answer. 32. Okay, we messed up somewhere. Okay, he wanted to give us some grace, yeah. So this is bytes, and again you should multiply with 8. 25600. So C is your answer. Yeah, that is honestly admirable from the gate paper setters. Okay, I'm sleepy and I will sleep. Good night.